Good afternoon, ladies and gentlemen. Welcome to the Quantum Computing Seminar, the first edition, which is named Discrimination of Quantum Operators. During the talk, we will present two methods of validation quantum architectures, the symmetric discrimination of quantum operations and the asymmetric one, known as the certification. The presentation begins with an overview of the discrimination schemes for quantum states, unitary channels, and general channels. Next, the focus will be mainly on discriminating schemes for the von Neumann measurements. We will discuss the theoretical approach to these problems and their implementation on quantum gate-based computers using the Qiskit platform. The speaker today is Paulina Lewandowska. Paulina Lewandowska has a master's in mathematics and young PhD in computer science. She has completed her PhD at the Institute of Theoretical and Applied Informatics of the Polish Academy of Sciences. At the same time, she was also one of the members of the Quantum Systems of Informatics group, members in Polish Academy of Science. There she has gained knowledge about quantum computing, benchmarking, and validation methods of gate-based quantum computers. Her research also includes quantum causal structure theory, quantum learning, and recently quantum game theory. Recently, she joined the Quantum Computing Lab at IT for Innovation's National Supercomputing Center to deepen her quantum computing experience. Thank you all for coming to join us today, and also thank you, Paulina, for your talk.
Okay, thank you. My name is Paulina Lewandowska. I am young doctor of computer science. I have graduated my PhD around 6 months ago, and then I'm so happy that I gave the opportunity to continue my research here at IT for Innovations National Supercomputing Center at Quantum Computing Lab. And today, I will be talking about discrimination methods of quantum operations. But before we start, I would like to say thank you. Thank you for coming, for register online. I would like to thank you, Marek Lampard, who gave me the opportunity to have a talk today, and all of you. But I think there is one more guy I should say thank you. This guy is, of course, Richard Feynman, one of precursor of quantum computing and quantum information theory. Thanks to him, we can meet here together. And he expressed the idea that quantum computers can be more efficient, solve some kind of problem, which the classical one could not. The most known problem is, of course, factorization problem, which can be solved efficiently by Shor algorithm. This seminar idea paved the way toward the building, toward the developing the first quantum devices. Such devices are called noisy intermediate scale. Noisy means that we can observe, unfortunately, some kind of noise during our calculation, whereas intermediate scale means that we have limited amount of qubits ranging from a dozen to few hundred. Of course, for such huge composite number, for example, Shor algorithm needs much more qubits, which nowadays the vendors are able to offer, but without a doubt, NISQ era is a huge step towards to building more and more powerful architectures. In this presentation, I will mostly focus on the gates-based quantum computer. So now I will briefly recall how such a computer works. The computation on quantum architecture can be divided into 3 parts, similar in our classical world. Classically, we have some input data, which are represented by the sequence of bits. The next step is the data processing, our algorithm, and the results are also represented by some bits as our output data from algorithm. Now, in our quantum world, our input data will be represented by some quantum state psi. Data processing can be treated as a state evolution, which are represented by the sequence of unitary gates. And finally, if we want to obtain some result from our circuit, we need to prepare some quantum measurement, and our output data is exactly the classical label obtaining some measurement outcome. Unfortunately, as I mentioned before, during our calculation, we can meet some kind of noise. This kind of noise can be caused by decoherence, the phenomena which is related with our environment, which is related with quantum devices, with our environment, or imperfect implementation of quantum gates or measurement. So we are not pretty sure which of operation was used during calculation. And this is exactly discrimination task. In this presentation, I will focus on the binary discrimination task, which we are not pretty sure which of operation was used during calculation, but we will choose between two of them. This on this figure, we can see some scenario for which we are not pretty sure which of quantum measurement, P1 or P2, was implemented during our circuit. And the task of discrimination is twofold. First of all, we would like to construct some optimal scenario which gave us the answer which we can be sure which of operation was used during calculation. If it's not possible, we would like to construct some scenario for which we achieve the maximum possible probability of correct discrimination between them. Moreover, we would like to calculate the exact theoretical value of such probability, but as we can see on the next slide, it will be also some complex task. Before we start talking about the result, I would like to introduce some notation and mathematical basic definition. Of course, I will use the Dirac notation. So the column vector from the complex Euclidean space X will be denoted by ket, whereas the row vector will be denoted by bra. The overlap between two vectors are called brackets, which can be some complex number, whereas the ket bra is an operator from the set of all matrices, which we will be denoted by L of X. Of course, the first step of our calculation is to prepare some initial state. Mathematically, the pure state can be treated as a normalized vector from the complex Euclidean space, or equivalently as a projective operator created from our vector psi. We will also use some mixed state, which is a convex combination of pure states. What it means that all of scalars alpha I is greater or equal to 0 to sum up to 1. What it means? It means okay. It means that each of eigenvalue of quantum states are non-negative, and there are to sum up to 1. And by omega of x, we will be denote the set of all quantum state. The next step of our calculation is to prepare some state evolution, and mathematically, the operation which map one state to another one even if we change the dimension of our system, is known as a quantum channel. This is a linear map, which is completely positive and trace preserving. And this is the most wider definition of state evolution of our quantum state. In my presentation, I will distinguish unitary channel and will denote it by psi u, defined by equation 2. And finally, to obtain some classical information about our system, we need to prepare some quantum measurement. The most general form of measurement is called POVM, positive operator value measure, which is the collection of positive semi-defined operator EI, which sum up to identity. Each of those matrices are called effects. And now we will distinguish two cases. The first cases will be in this presentation in general form of quantum measurement will be represented by the P, whereas if we will talking about the measurement in computational basis, we will use the notation given by the figure 2. And the most crucial statement in quantum physics, in quantum information, is to say that the probability of obtaining some classical output label I is given by the following trace given by equation 3. This is exactly the overlap between our quantum state rho, which describe our quantum system, and corresponding effects EI. In this presentation, I will focus on the special class of quantum measurements called von Neumann measurements. Such measurements are projective, has a projective operator. Each of our effects are projective operator with rank 1, yes. And then every von Neumann measurement can be parameterized by some unitary matrix U. That means each effect is created, but using the column of some fixed unitary matrix U and creating the projector of this column. We can observe that if we fix the unitary matrix U, which is equal identity, then we simplify our problem to the measurement in computational basis. Why we choose von Neumann measurement? The answer is pretty simple, because nowadays the vendors offer just preparing measurement in computational basis. We are not able to prepare any other measurement, but as we can see on this figure, we are able to decompose every von Neumann measurement by implement first the corresponding unitary matrix U dagger, and then preparing the measurement in computational basis, which this operation is available on hardwares. In the problem of discrimination, but not only, a very useful tool is exactly numerical range. Numerical range of square matrices I can be defined as a complex plane, complex subset of complex plane defined by equation 5. The numerical range and its generalization and usefulness you can read. You can see also on the website numericalshadow.org. I will present this website because I am one of co-author of this website together with my friends from Poland. So I really recommend it. But numerical range play a crucial role, for example, in error quantum correction, discrimination and certification of quantum operation, or perturbation of quantum operation. And in quantum physics, the numerical range contains all possible expectation value of A. And researching about the numerical range sometimes is simpler than the research about the spectrum of some matrices. To try to make this definition more familiar, I would like to present some properties about the numerical range. Due to Hausdorff-Toeplitz theorem, numerical range of any square matrix A is convex subset of complex plane, or also compact, and contains the spectrum of A. Moreover, if our matrix is normal, the numerical range creates the convex hull of a spectrum of our matrix A. If we will consider the Hermitian matrices, the numerical range creates interval in the real axis from the minimum eigenvalue to the maximum one. Here I would like to present some example of numerical range for some non-negative and for some non-normal and normal matrix. The first picture represents the numerical range of non-normal matrix X. Of course, we can see this numerical range is compact, convex, and contains all eigenvalues of matrix X, which are represented by the green stars. Whereas on the second picture, you can see the numerical range of normal diagonal matrix X. If matrix is diagonal, then on the diagonal entries, we can see the eigenvalues of such a matrix. So our spectrum is equal 1, -1, I, and -I. And as we can see, the numerical range creates the convex hull of such a numbers. I think that's enough for the preliminaries to start talking about the result. So let us first consider the problem of discrimination of quantum states. So now we can imagine the situation that one of two quantum states was hidden into our circuit, but we are not sure which one was used. And we would like to calculate the probability of success discrimination between them, given by some maximization over finite over final measurements pi with two effects E0 and E1. And this is exactly the maximization given by equation 6. And moreover, we would like to discover how this measurement looks like. And the answer of these two questions are hidden into the Holevo-Hellstrom theorem. The Holevo-Hellstrom theorem say that the probability of success discrimination between two quantum states is upper bound by the distance between quantum channel in trace norm. This is the upper bound, but moreover, we can also prove that there exists some measurement, some projective measurement for which this inequality is achieved. This measurement will be exactly our optimal final measurement. The first obvious fact or obvious observation from this theorem is that if we take two orthogonal states, the distance between them in trace norm is equal to, and then we have the perfect discrimination between them. It implies that if we will try to make our quantum states be more and more orthogonal, then our probability of success discrimination will be increased. But I have decided to show the proof of Holevo-Hellstrom theorem because then was hidden how the final measurement looks like. First, let us define two operators, rho and x, given by equation 8. And now we just rewrite our quantum states ρ0 and ρ1 by using operator rho and x. And then we would like to calculate the following trace given by equation 10. This is exactly the same formula as previous, which we have on the equation 6. So the formula for the calculation optimal probability. And we rewrite our problem to equation 10. And now it's enough to use Holder inequality for the norms and observe this condition that the distance between two effects in the infinity Schatten norm is upper bound by its sum. The sum of two effects is equal identity. So the infinity Schatten norm of identity matrix is equal 1 because recall the infinity Schatten norm give us the answer about the maximum singular value of given matrices. And now we obtain our upper bound. To show that this inequality is achieved, let us use the Jordan-Hahn decomposition of Hermitian matrices. So we take our operator X, which is the subtraction of two quantum states. Of course, the subtraction of two quantum states is also Hermitian because the eigenvalue are still real. And then we decompose this matrix X by P minus Q, where P and Q is a positive matrix such that P times Q is equal 0. And then let us take our effects E0 and E1 by the projector onto the image of matrix P. And if we defined in this way our effects given by equation 13, then we can observe that E0 and E1 creates a projective measurement. And they are sum up to identity, and each of them are projective operator. And then if we take our effects to calculate the trace, it will be equal exactly the trace norm of operator X, which is exactly equal the distance between two quantum states. So the main step of this construction is to take a matrix X and then using Jordan-Hahn decomposition, we take the projector onto the image of matrix P, and that's it. For now, let us consider a more complex task, which is discrimination of quantum channel. And now let us observe that we include some auctional system, and we assume that our quantum states, initial quantum state psi0 can be entanglement. And again, we would like to first of all calculate the probability of success discrimination. And for now, it will be double maximization over all initial state and over all final measurement Q. This maximization is given by equation 16. And now, the direct analogy for Holevo-Hellstrom theorem for quantum channel is that the probability of success discrimination of two quantum channel is also given by the distance between quantum channel, but now in the special norm for quantum mapping, which are called diamond norm. The diamond norm is a maximization over all pure quantum states of this formula, of this trace norm. But it turns out that even for a really small dimension of our quantum channel, it's the theoretical calculation is almost impossible to develop, and moreover, the numerical investigation are also really complex task. The most practical methods for numerical calculation, the diamond norm, is to use the semi-defined programming. And here I will present the semi-defined program, the dual and primary problem for the calculating the diamond norm for all hermiticity preserving map. What means that such a mapping maps all Hermitian operator to another one with joint operator M. And for Slater theorem, we can, for this problem, we can treat primal and dual problem equivalently, but even with these informations, sometimes this problem are very complex to compute. So we would like to omit some numerical obstacle, and even for some kind of quantum channel, we would like to calculate the diamond norm and the probability of success discrimination. And it turns out that for unitary channel, the diamond norm, the value of diamond norm is strictly related with the numerical range. So let us consider the scenario for which we would like to distinguish between quantum channel psi U and quantum channel psi identity. And then let us consider the numerical range of matrix U dagger, and for simplify, let us assume that U dagger has an eigenvalue as follow, and then here the red triangle represents the numerical range of unitary matrix U dagger, and then it's enough to calculate the value Ni, which is exactly the distance between 0 and numerical range of unitary matrix U. This is Pythagoras theorem, just Pythagoras theorem, and then if we calculate this value, we immediately are able to calculate the diamond norm between two quantum channel, unitary channel, and observe if 0 belongs to the numerical range of unitary U dagger, then we have a perfect discrimination between quantum unitary channel psi U and psi identity. So our second observation is if we will try to move close to 0 from our unitary channel U, then the probability of correct discrimination will be increasing. And now let us move to the problem of discrimination of quantum von Neumann measurement. And this scenario is similar as previous. We have some we have some one of two von Neumann measurement, and now and also we would like to discover the initial quantum state and the final measurement VI. And now we can observe that the formula of our problem doesn't change because the probability of success discrimination is also distance in diamond norm. But as I mentioned before, we are not able to do anything with them. So our first step in this problem was we reformulate our the distance between two von Neumann measurement to some minimalization over all diagonal unitary matrix and to calculate the diamond norm between unitary channel, which are pretty known by using the definition of numerical range. It will be our first step to simplify our problem. But then if we trying to simplify this formula, we rewrite our problem to some maximization over all a diagonal unitary matrix and minimalization over all quantum state rho of such terrible function depending on trace. And the crucial point of this paper was to prove that this function, this trace, has a saddle point, and then we were able to change maximum, minimum to minimum and maximum, what immediately simplify our problem because maximum over all diagonal unitary matrix of this formula is exactly can be presented like this sum, which is this sum is exactly trace norm of diagonal matrix rho U dagger. This is exactly taking the unitary the diagonal entries of the matrix U dagger rho and calculate the trace norm of it. Of course, still under the assumption over all quantum state rho. So we were able to simplify our semi-defined program to calculate some pretty nice minimalization over all quantum state. What was next? Of course, we would like to discover the components of optimal strategy. So first of all, we would like to discover our initial state. This is some ugly proof, but with a pretty nice geometrical representation. But we divided our problem into two parts. The first part was when we have perfect discrimination between our von Neumann measurement, and it can happen if and only if there exists some state, quantum state rho, such that the diagonal entries of unitary dagger rho is equal to 0. And then for such quantum state rho, we can take the discriminator of our problem as the vectorization of this matrix. But what if we don't have perfect discrimination? And now assume that our the matrix E0 is exactly this matrix which minimizes the trace norm between quantum unitary channel. And let us see how we now can construct the discriminator. First, we assume the numerical range of this matrix. And now we find the most distant eigenvalue of our matrix U E0 dagger. And then we take these eigenvalues and creating the projector onto the corresponding eigenvector of these eigenvalues. And then we create the state rho as 1/2 projector onto the minimum eigenvalue and 1/2 the projector onto the eigenvector of minimum maximum eigenvalue. And then after vectorization of this matrix, we can fix this matrix as our discriminator. But how to calculate the final optimal measurement? As previous, we use the Holevo-Hellstrom theorem, for which we describe the matrix X by taking our discriminator and applying on it the measurement PU and P identity. And then we also use the Hahn-Jordan decomposition and create the projector onto these matrices. And then we define our measurement by taking this corresponding matrices. As we can see later, it will be not some complicated for some example. But having everything, having the knowledge about the theoretical approach, we have created PyQbench, the Python library for benchmarking gate-based quantum computer. This library is available of a Python package index by using pip install PyQbench. Everything which is connected with PyQbench can be found on GitHub, on our documentation or archive. So I really invite you. But few words about PyQbench. PyQbench benchmarks based on the scheme of discrimination of von Neumann, but qubit measurement. And PyQbench give us possibility to test various architecture available through Qiskit, of course, IBM Q, and Amazon Braket, the architecture like Rigetti or Lucy. PyQbench offer a simplified, ready-to-use CLI for running benchmark using predefined by us family, Fourier family of measurement. But for any other scenario which you imagine, PyQbench can be used as a Python library. In this presentation, I've just focused on the how the CLI works, because it's pretty friendly user for everyone, even if you are not very close to my research. So let us define the predefined family of measurement we would like to distinguish. For now, the problem of discrimination will be discrimination between measurement in computational basis of the measurement in the basis of U given by equation 28. And we can calculate it that due to the previous consideration, that for all these cases, the optimal initial state, our discriminator, is given by the maximal entanglement state, whereas the final measurement are given by the matrix V0 given by equation 13 and V1 given by creating by the changing the column of the matrix V0. And then for such define the von Neumann measurement, the probability of success discrimination between two von Neumann measurement is given by equation 31. So for the qubit case, we didn't calculate the semi-defined program, but we were able to calculate the exact value of such a probability. So we have almost everything to implement of real hardware, our algorithm. We have initial state, which is maximal entanglement state. We have von Neumann measurement, which we would like to discriminate. And we have V0 and V1, the conditional measurement. But we are nowadays, the vendors don't offer us to implement the controlled measurement. So we need to find some methods how to implement exactly such a operation. And we proposed two methods. The first method to omit our obstacle was to use post-selection, whereas the second one is to use direct sum. Now I briefly describe how the post-selection works. So now our experiment can be described by the four-element tuple P, PU or P identity, one of two measurements, I, J, and K, which is equal 0 or 1, because this is qubit gate. And now we run 4 cases of circuit. First, we run U and V0, U and V1, identity and V0, and identity and V1. And if we want to simulate the controlled measurement, we discard all the cases for which E is not equal K, because we would like to exactly have the situation for which A is equal 0, and we implemented V0, and the same for the E is which will be equal 1. So the total number of valid experiment is given by equation 32. And now we assume 2 successful cases. The first successful cases is then if J is equal 0 and we implemented the measurement in basis U, or if J is equal 1 and we implemented the measurement in computational basis. And now the empirical success probability can be computed by using equation 35. How the direct sum approach work? Now we implement the direct sum operator of our matrices V0 and V1, and now we run 2 cases. The first cases is our algorithm with implemented unitary gates U, and then with identity. So now the number of valid experiment is exactly the cardinality of this set, whereas the number of successful trials for measurement PU and P identity is given by equation 36 and 37. So the empirical probability of success discrimination can be computed as previous. So if we have all components, I will briefly present the workflow of CLI. So first, we would like to prepare the backend, which we would like to use during our calculation and our experiment. And the next step will be run our experiment, and depends on backend. Sometimes we will able to run our experiments in asynchronous mode, what means that we send our job to the platform and we can switch on off the computer, go to home, and not be afraid that if something went wrong with our script will interrupt. We lost some data, what means we lost our money because we already ran some experiment, but we didn't save our results. So if it's possible, I recommend the asynchronous mode. And then optional, if we change the asynchronous mode, then we receive from our program the intermediate data, and we are able to change the status of our submitted job. And if the status will be done, we are able to ask the platform, hello, give me my result back by resolving a job to actual measurement outcomes. And finally, we would like to present our result in some tabulate. So how define the experiment file and backend? We will use the YAM format. So first, we define the experiment of the left side. And here we write type, discrimination Fourier, because PyCuBench allow also the benchmark based on the other scenario, qubits, the pairs of qubits which we would like to use during calculation. And now it's worth to noting that PyCuBench is pretty clever because if the user give PyCuBench some qubits which are not connected, PyCuBench say, no, we are not able to do that. And due to that, we don't lose the money because we avoid the situation that we pay for some jobs which are not possible to run. And next is the angle definition of our Fourier family of measurement. This is definition of angle which we would like to manipulate. And next, we choose the gate set, IBM, Lucy, or Rigetti of so on, because it's very important that PyCuBench use just native gates. So architecture don't need to compile itself. This is really important because sometimes the compilation of hardware are not optimal. And method direct sum or post-selection, and the number of shot per circuit. And here we define the backend YAML. I will choose the IBM Q Calcutta with 27 qubits. Here, for example, I choose the synchronous mode. So I fix the asynchronous to false. And the next is to give the information about the provider, which are available on website or documentation, IBM Q or Amazon Braket. It's really important to fulfill this in the correct way. So if we have some experiment file and backend, to run PyCuBench is really simple. We just open the terminal and write QBench, disk Fourier. This is our benchmark type. And if you want to run our benchmark, it's enough to write benchmark, experiment file, backend file, and as an output, I note as a synchronous result YAM. How this file looks like. This is, of course, just a small part of result. Here we have some data about target which we use in our calculation, ancilla, this is our qubits, the angle phi, which we define our family of Fourier measurement, and the result per circuit. And now, for example, if we implemented the identity matrix instead of the measurement in basis U, and here we have exactly the output of our results. This is histogram of measurement outcome, and now it's quite interesting information that PyCubench allow also some kind of error mitigation by using M3 error mitigation package. So this mitigation info are necessary to use this package. And here we have mitigated histogram after implementation M3 error mitigation in our problem. If we choose the asynchronous mode, for example, like that, first we obtain some metadata about our experiment and backend. And what is important, our job ID. This is some unique name of our experiment. And if this job ID, we can check if our experiment is done by using the command kubench disk Fourier status. Then we are able to resolve our problem, and our resolved file should be looks very similar to the file from synchronous mode. And finally, we use the command kubench disk Fourier tabulate to present some results in CSV. File. And now again we have information about target, ancilla, the angle psi, the theoretical probability which we should obtain from architecture, the empirical probability, and the probability after using the package M3 error mitigation. Here we can see the result from the machine IBM Q Kolkata with 27 qubits. I ran this experiment on 3 pairs of qubits, 0, 1, 1, 2, and 40, 60. And the theoretical probability is given with a black line, whereas the red line represents the empirical probability, and blue line represents the probability after using the package M3 error mitigation. The results are after or before using the package M3 error mitigation was quite similar. But what is interesting, that for example, for experiment which was prepared on qubit 1 and 2, even if vendors promise that these qubits are connected, I have checked that the CNOT gate, just 2 qubit gates proposed from IBM, the error gate of the CNOT was equal 1. What it means that we weren't able to entangle our state. So we need to pay attention about the specification of the architecture in such moments, because the parameters of our architecture change in time and all the time. And the question is, is it possible, and if yes, how to implement the discrimination scenario, but not for qubit measurement, but any dimension, or is it possible to implement some other scenario connected with discrimination? I think there are lots of questions in this direction we can imagine. Thank you for your attention.
Okay, thank you very much for your talk. It was really impressive. I have a very long list of notes that I would like to ask. But first of all, I would like to ask to anyone to ask for the questions.
I have one question. Forgive me, might be a bit silly question, but is it tied to some specific architecture like superconducting qubits or photonic qubits?
We benchmark the architecture from IBM, Lucy, and Rigetti. Yes, this is three of them which we were interested in because we gave the access from them.
But what's your feeling? Do you think that it is possible just to move to the ion trap technology, for example?
I think, of course.
Okay, next one.
Well, you said that you used M3 for the noise mitigation.
Yes.
Why did you choose specifically this method? Is it because it is implemented with Qiskit, or did you have any other reason for choosing specific?
The PyQbench is still developed, and we would like to implement the other quantum error correction methods, mostly due to the work of other PhD students in my previous work. But it was one of the simplest way to first step for quantum error mitigation of this problem.
Okay, thank you.
Okay, before asking another question, can you go back to slide 40?
Oh my God, 40.
Yes, of course. I have a direct question. Yeah, this is quite impressive. This is case number 212.
Yes.
As you said, that this is due to the architecture.
Yes.
Can you tell us something more about how you solved this problem?
In general, we send this task to them, but it happened that, for example, we can meet this problem, and one half next, the problem is changed because this error gate and a lot of parameters are changing extremely fast. Yes.
So it was solved by IBM somehow.
Yes, this is IBM architecture.
Yeah.
Yes.
So there is nothing tricky in PyQM to overcome this problem.
I think without entanglement we are able to do nothing. Yeah. So without just two qubit gates, our qubits are not connected at all.
Okay, I know really that I'm diving into details because that's what I'm really interested in. So we can maybe discuss later and continue with it. So please feel free and continue with your questions. Any questions here? One more, please.
I just have one small remark. For this problem, it is often a good practice to look up the qubits and the architecture and look at the parameters that IBM updates regularly.
Yes.
And based on that, choose the ideal pair for your calculations.
Yes, exactly.
Yeah, but that's what I was thinking about. That you have to select with respect to the architecture. Mm-hmm. Yeah. Okay, if there are no more questions from our listening friends, I'd like to use the word QUENTS. It is a shortage of Friends of Quantum Computing from the air. And then if there are no more questions also here in the classroom, then I would like to thanks to Paulina once again. And I would like to welcome you for the next event that will be in April, and it will be officially announced soon. And the next speaker, Martin Beseda, will tell us more about some applications in quantum chemistry. So that's all for us at this moment. Thank you very much for your time.